Back, and today let's solve Leetcode problem 33 titled Search in Rotated Sorted Array. So there is an integer array nums sorted in ascending order with distinct values, something very important to note. So prior to being passed to our function, nums is possibly rotated at an unknown pivot index k, where k is in bounds of the length of our input array nums and is greater than or equal to 1, such that the resulting array is nums of k plus 1, and so on and so forth until nums of k minus 1, and it's going to be 0 indexed. So for example, the input array for context 0, 1, 2, 4, 5, 6, 7 might be rotated at the pivot index 3, and then if we rotated it around pivot index 3, we would get a result of 4, 5, 6, 7, 0, 1, 2. And the reason why is because if we rotated this array around the pivot index of 3, then this index 3, 4 would become the new initial element of the resulting input array, and all the elements before it would be tagged on at the end of it. So we'd have 4 through 7, and then these initial elements with their relative order would be added at the end of the array to get a resulting array of 4, 5, 6, 7, 0, 1, 2. Where again the pivot index is the new index or first index, and that's going to be the value nums at 3, which is going to be 4. So we're given the array nums after the possible rotation and an integer target, and we need to return the index of target if it is in nums, or -1 if it's not in nums. And we must write an algorithm with big O of log n runtime complexity. So two things. If we didn't have this line of constraint here, this would be an easy problem or just too easy for Leetcode. And the reason why is because, let me just quickly delete this code, right? And the reason why is because if we wanted to solve this problem in linear time or big O of n time, we could just loop through the array in a big O of n linear time iterative solution, keeping track of the current index, and if the current value matches the target, we can return the index, but if we never find it to match, we can simply return -1. That is a linear time solution. But we are tasked to solve this problem with an algorithm in big O of log n runtime complexity. And usually, a quick tip for you guys, when you see big O of log n runtime complexity, 95% of the time, it's hinting you that it's going to be a binary search algorithm. And in this case, it is. But before we get too deep into that, let's first look at the examples and see how this problem really works out. So, in example 1, we have our input array nums to be 4, 5, 6, 7, 0, 1, 2. As you can see, it was most likely, or rather not most likely, but it was definitely rotated around the pivot index of 3, and so 4 is the new initial element, and our target is 0. In this case, that 0 after this possible rotation would be at index 4, and so we're going to return the index of its placement in the new input array nums, again after that rotation. In example 2, our target is 3, but notice how 3 isn't even an element in this input array. No matter how many rotations we make, there is no 3, and so we can never get a value of 3, and so we're going to output -1 because, again, 3 does not exist in this array. And finally, in example 3, our target is equal to 0, and we only have one element of length 1 in our input array nums, and it's not 0, it's 1, and so the target number still isn't in our input array nums, and so for that reason, we also still output -1 for this test case as well. So for the length of our input array nums, it's not going to exceed 5,000, and it's going to be at least 1, and any value nums at index I in our input array nums is going to be between -10 to the power of 4 and 10 to the power of 4. And again, we're guaranteed that all the values of nums are unique, and it is ascending, that is possibly rotated. So with these constraints out of the way and these examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and to think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so what are some key observations we can make in this problem to help us really solve it efficiently? Well, the first one is we know that this array is sorted in ascending order. Okay, and we know that it is rotated at some pivot index k. Okay, and so the observation we can make is that even though this input array, even though it's going to be sorted at least one part, either the left half or the right half, at least one of those parts is always going to be sorted, regardless of how our rotation is. And this is very important to solve this problem efficiently using that modified binary search approach with that log n runtime complexity that the problem is really asking us to solve. So again, we're going to use a modified binary search algorithm, and the kind of high-level rundown of how we're going to do it is like we usually do for binary search. We're going to start with 2 pointers. Left is going to be at the start of the array at index 0, and right is going to be at the end of the array at index -1 in Python. And while left is in bounds of the right pointer, basically meaning while left is less than or equal to right, we want to first find the middle element using the formula left plus right divided by 2 with integer division. And first, we have to check, does the middle element, does it actually equal to the target like we usually do for binary search? If it does, we have to immediately return that middle index and just break out. Otherwise, we have to actually decide where to search. This is the modified part of this binary search. If the middle element is not equal to the target in that iteration, again, we need to decide which side we have to actually search. And again, one observation to make here is that either the left half is going to be sorted or the right half is always going to be sorted. And if the left half is sorted, well, then we have to actually check if the target actually lies within that sorted range. If it does, we can update or move the right pointer to mid-1, searching for the left half. But if it's not, we have to search in the other half by moving the left pointer to mid+1 to go to the right half. But if the right half is sorted, then we have to similarly decide whether to search the sorted half or the left half. The sorted right half, rather, or the sorted left half. However, if the target is never found in this loop, well then we're just going to return -1 because that's exactly what the problem is asking us to do. So with this kind of high-level rundown out of the way, let's go ahead and dive straight into the code here. So I'm actually going to initialize my 2 variables left and right for this binary search approach. I'm literally just going to call them left and right here. And I'm going to initialize them to 0, and the length of our input array nums -1. Right, 0 is simply going to mark the 0th or initial index, and length of nums -1 is going to mark the last index, right, the beginning of the array and the end of the array, which is simply going to help us kind of narrow down the search range of our input. Right, that's literally why binary search is very efficient, along with this continuous halving of ranges. Okay, so while left is less than or equal to right, basically that what we're really saying is while we're actually saying that the left pointer is less than or equal to the right pointer. If it surpasses right, then we know we've exhausted all the possibilities, and that means the target isn't in the array. And if that's the case, well, then we simply have to return -1. So while this is the case, we want to get our middle index in this iteration. It's going to be left plus right divided by 2, whatever their values are in this iteration. So left plus right divided by 2. I'm going to space them out for readability here. Integer division by 2, and in Python, integer division is just these 2 slashes here. Usually they're comments in other languages like Java and C++, but in this case, it's just integer division for Python. Now, the first case, like we usually do for binary search, is the current value equal to the target? If it is, so if nums at mid, in this iteration, if it's equal to the target, great, we don't have to do any more computations or operations. We've found the target, and we simply have to return its index mid, whatever it is in this iteration. Okay, because of course that's exactly what the problem is asking. If we found the target, great, just return it. Okay, return mid. However, if it's not the case, this is where we start looking at which left or right sorted half to actually look for based on the current situation of the pointers and the target value. So the first base case, or rather the first conditional that we're going to have here, is if nums at the current left index, if it's less than nums at the current middle. And what we really are checking here, this is very key. Why do we do this? Well, this is where we're actually checking if the left half of the array is sorted. And this is true, again, if the value at nums at left is less than or equal to value at nums at mid. And pardon me, I forgot my equal to sign here. And if it's less than or equal to nums at mid, right? And one observation, again, that we can make here is that in a rotated sorted array, one part is always going to be sorted. Whether it's the left part or the right part, one of them is always going to be sorted. And here we're checking, in this specific conditional, if the left half is sorted. So if nums at left is less than or equal to nums at mid. Okay, that kind of confirms or validates that conditional check. Now, if this is the case and nums at left is still less than or equal to the target, which is still in bounds of nums at mid, so it's less than nums at mid. So if it's actually within this search range, the target value, if that's the case, we can update right to be equal to mid minus 1. And what we're really doing here in this conditional, if nums at left is actually less than or equal to nums at mid, is here we're checking, well, does the target actually lie in the left sorted half? If it does, well, great. But if the target is greater than or equal to nums at left, and it's less than or equal, or rather just strictly less than nums at mid, that means that it's in the range nums left and nums at mid. It's in this range, and so we want to check the sorted left half. This is where we're literally checking if the target is in this left sorted half. And if it is, well, then we want to go to the left. We want to search in the right, in the left. And so we update right to be mid minus 1 to go to the left half. So if the target is actually in the sorted left half, we want to update our right pointer to discard that right half, right? That's one of the more reasons why binary search is so efficient. Now, if nums at left is not even less than or equal to nums at mid, that means the left half isn't sorted. And if the left half isn't sorted, then we know that the right half has to be sorted. Because again, in this rotated, originally sorted ascending order array, one half is always going to be sorted, whether it's the left or right half. So else, in this else conditional, if this doesn't hold true, that means the right half is sorted instead of the left half. And so if that's the case, if nums at mid is less than target, which is still in bounds of nums at right, in this case, less than or equal to sign is at nums at right, another observation to make, well, then we want to search in the left half. And so we want to update, or rather, we want to search in the right half. So we want to update left to be mid plus 1. Discarding the left half in this case and searching in the right position. So updating left to be further right. Meaning, if the target is actually in the sorted right half, update the left to search there. And what this conditional really checks is if the left half isn't sorted, well, the right half must be sorted. And so we have to check, well, is the target actually in the sorted right half? If does it actually lie in the sorted right half? And effectively, if we never return mid, well, then we would just want to return -1 outside of the while loop once it's done executing, because if the loop ends and we still didn't find the target, that means the target simply isn't in the array. We've exhausted all possibilities. Left is no longer less than or equal to right, and so we can just return -1, indicating that the target isn't even in our input array nums, and we never found an index to match it, either in the left half or right half, based on our 2 pointers left and right. So unless I made any syntax errors here, this should be accepted and it should be a valid solution. Okay. Sorry. I don't know why I spaced the less than or equal to sign. Now this should be a valid solution. Now this should be accepted. And it's just judging. Let's just wait for it to judge. Let's see if I made any spelling mistakes here. I probably did. Okay. Less than or equal to nums at mid. Target, which is less than nums at mid, right, is equal to mid minus 1. Oops. So it looks like I actually forgot the conditional. So left to be equal to mid plus 1. So what left is equal to mid plus 1 really does is in this conditional, well, going back, if the target isn't in the sorted left half, we actually have to move the left pointer to mid plus 1, because we know, although nums at left is actually less than or equal to nums at mid, if nums at left is not less than or equal to target, which is in bounds of nums at mid, that means the target isn't actually in the sorted left half, and so we have to actually search in the right half instead, and so we do that by simply incrementing our left pointer to mid plus 1. Okay, that's basically what that conditional checks. And now, I think this should be a valid solution. Sorry about that, guys. Let's go ahead and check this, unless I made another syntax error here. And yeah, okay, same thing here. So else, I forgot to say right is equal to mid minus 1. Similar logic here. If the target isn't in the sorted right half, then we have to move the right pointer to mid minus 1, because that means although the right half is sorted, it's not, the target value isn't in the sorted right half, and so we want to search in the left half of this range instead. And now, sorry about that, this should be a valid solution, and as you can see, this is just about as efficient as you can get. So, for a quick high-level rundown, how does this algorithm actually work? So basically, we're using binary search to repeatedly divide the array into 2 halves. And basically, by observing which half is actually sorted, we're determining where the target might lie and narrowing down that search range based on the left or right half, based on where the target value lies, very efficiently. And if the target is actually found, we can return its index once we actually hit this conditional here. But if we never found it, we can simply return -1 outside of the while loop, indicating that it isn't even in our input array nums. So for the time complexity of this solution, this is going to be a big O of course, log n solution. It is just the binary search algorithm like the problem is asking us to implement. And the reason why is because each step or iteration of this binary search actually halves the search range. It turns it into half. And so the algorithm does run in logarithmic time. And for the space complexity, believe it or not, this is going to be a big O of 1 or constant time solution because we're not actually using any auxiliary memory here or any extra data structures. We're really only using a few integer variables like left, right, and mid. And so we don't actually, again, require any extra space. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. Sorry about the errors here in my code. I forgot to just add a couple lines. But if you guys, again, enjoyed this solution, please consider liking this video. And without further ado, I will see you guys in the next video. Bye-bye.